Hello, I'm Wanpeng Li from Tencent Cloud. I'm an active KVM contributor in the KVM community. Today, I will introduce the solution to boost the dedicated instance via KVM text cut. This is today's agenda. All the features are upstream now, except the last one, halt-polling guest, is from Marcelo. Other patches are pushed to upstream by me. The motivation of Exitless Timer is both ARM timer and timer fair can incur vmexits. Dedicated instance can encounter performance jitter if the workloads are sensitive to the vmexits. So there are two vmexits here. The Exitless Timer can cut the second half. We can implement the injection Exitless. We utilize the housekeeping subsystems to cooperate with KVM subsystems to offload the local APIC timer emulation to the housekeeping CPUs. After we enable housekeeping subsystem, the CPUs are separated to housekeeping CPUs and non-housekeeping CPUs. The emulated local APIC timer, which can be emulated by the HR timer on host, is offloaded to the housekeeping CPUs, and the VM is running on non-housekeeping CPUs. The expire timer interrupt fair on the housekeeping CPUs and injected to the VM by posting interrupt from the housekeeping CPUs. The host admin should fine-tune the host, like enable no hertz full, and also keep the CPU in non-root mode as possible as we can. For example, disable some instructions vmexits. The normal kernel KVM interrupt delivery, the external interrupt will be happen on the housekeeping CPUs, and the vCPU will vmexit due to this external interrupt. But after Exitless Timer, the external interrupt is on the housekeeping CPUs. The timer interrupt is injected to the VM from the housekeeping CPUs to the non-housekeeping CPUs, which the VM is running on. Let's see the performance number. The percent of external interrupt vmexit time can be reduced from 39% to around 3%. Next one is Exitless Timer, Exitless API. Local APIC is the interrupt controller in the CPU, and the X2 APIC physical mode is commonly used for the local APIC. When one CPU send API to the target CPU, the OS need to write to ICR registers. Each write to ICR registers in the local APIC will cause a vmexit. So multicast APIs and the function call APIs make it worse when scaling to larger VMs. The Exitless API can set the destination APIC IDs in one bitmap. Then we use a hypercall to send this bitmap to the hypervisor. KVM can scan this bitmap to send APIs to target CPUs. And one bitmap can service at most 128 target CPUs. So we can save the vmexits. Let's see the performance number. We test on Liang Skylake server, 2 socket, 40 cores, and 80 threads. The API micro benchmark can improve by 54%. Next one is a capability to disable exits. Enable this capability. On a per VM, we can provide user space with a way to no longer intercept some instructions for improved latency in some workloads. For example, after we expose MWAIT to the guest, we can observe some product workload, the performance from 80% of bare metal performance to 95% bare metal performance. The hack bench time can be improved by around 1% if we are not in the cell pause loop. Because the VM has dedicated physical CPUs, we don't need intercept the pause loop exciting. Because both the log holders and the log readers can run simultaneously. So we can avoid the yield and the re-kick penalty by pause loop exciting. Next one is a dedicated performance hint. The hypervisor can give the guest a dedicated performance hint. If the guest is aware we have dedicated physical CPUs, the guest can enable some optimizations when running on the dedicated physical CPUs. For example, the guest can choose native qsmin log instead of perivert qsmin log. Because the VM has dedicated physical CPUs, the perivert qsmin log can incur halt and re-kick penalty. Next one is the guest can choose native TLB shutdown instead of perivert TLB shutdown. And also we can disable perivert scatter yield. The second one and the third one are introduced by me to optimize the CPU subscribe scenarios. So we don't need this on the dedicated scenarios. The fourth one is we can enable guest halt-polling in this case. I will introduce this later. Next one is adaptively tuned advanced local epic timer. The advanced local epic timer is originally introduced by Marcelo from Red Hat. I gave further optimization and add the adaptively tuned logic this year. The original idea of the advanced local epic timer is to hidden the overhead between local epic timer fares and before VM entry. For example, in this diagram, the emulated timer fare in time T2. But we go through a long way in the hypervisor before inject the timer interrupt to the VM in time T4. The guest can wear such timer delay between T2 and T4. Can we expire the timer interrupt in advance? For example, in T1, then we still go through a long way in the hypervisor. For example, in time T3, but we just have a small timer delay leave over T2 to T3. Expire in advance is good, but what's the best advanced value? Different CPU generations can have different VM exit and VM entry overheads. And different guest kernel and host kernel variants and kernel config can have different latency. So what's the best advanced value we should set? I introduced the adaptively tuned logic. It has an initial value. Then we adaptively tune the advanced value step by step smoothly. When the guest aware it is too early, the timer interrupt, it is too early, then we will reduce the advanced value. When it is too late, we can increase the advanced value. Let's see the performance number. I didn't enable the kernel preemption in both gas and host. The average cyclic test can be reduced from 9 microseconds to 5 microseconds. The last one is adaptively halt-polling in host and guest. Message passing workloads are mentioned by Rick from Facebook and Marcelo from Rick from Facebook and David from Google several years ago. Such kind of workloads can frequently switch between running and idle. Even driven workloads like LAMP servers, memory cache, Redis, SAP HANA are such kind of workloads. Another example is TCP/RR. Let's take TCP/RR as an example. The client and the server can ping pong 1 byte of data over an established TCP connection. The client sends 1 byte to server. It switches from running to idle. The server receives this byte and sends 1 byte back. It switches from idle to running. Then it switches from running to idle again. And also the client switches from idle to running. So the blue bar is vCPU is running, and the white margin between two blue bars are vCPU is idle. So such kind of workloads can frequently switch between running and idle. When the OS is idle, it will execute halt instructions which can trap to the hypervisor. The host scheduler can schedule the vCPU out. So there is a vmexit and the schedule out penalty. Can we optimize these two penalties? Maybe we can add some pool logic to the before schedule out, like something like an API in the network. So if the next interrupt arrive in this pool duration before schedule out, then we can VM entry immediately without schedule out. If in this pool duration next interrupt is not arrived, then we can schedule out. The pool logic is more suitable for the message passing workload. When or not, it can suitable for other scenarios. For example, idle Windows guest. The idle Windows guest still has periodic timer interrupt. It doesn't like Linux guest can have take list features. So the Windows guest, each time it handle the timer interrupt, then it will stay idle until next timer interrupt. So it can idle for a longer time. It doesn't like message passing workload, which will switch between running and idle frequently, so which has a short halt. The idle Windows guest has a long halt. So what's the best pool duration we should set? I add the adaptively pooling logic. The pool duration can be adaptively shrink and grow according to the history behavior. When we detect short halt, like the message passing workload, we will grow the pool duration aggressively. When the long halt is detected, we will shrink the pool duration aggressively. Let's see the performance number. The Apache bench can improve by 28%. As I mentioned before, there is still a vmexit. So can we avoid this vmexit? This year, Marcelo from Red Hat introduced the CPU idle halt pool governor and the halt pool CPU idle driver. Since it pool in the guest, it can avoid the vmexit cost, and it can also avoid sending an API when performing a wake up. So is there any drawback for this solution? Since pooling is performed in the guest, we cannot accurately aware whether or not there are other runnable tasks in the host currently. But the pool in the KVM, we can detect whether or not the scheduler run queue has other runnable tasks. If we have other runnable tasks on the scheduler run queue, we can stop pool in the host, but we don't know this in the guest. So this limit the available scenarios for the hot pool governor and the hot pool idle drivers. Now we enable this feature when the hypervisor give dedicated performance hint to the guest, which means that the VM has dedicated physical CPUs. Pool in the guest will not influence other VMs. Let's see the performance number. Pool in the ping pong testing. Pool in the guest has better latency than host, than pool in host, but a little worse than the native host, native bare metal. Yeah. Hello. So, is there any questions?
Hi, my question's about the exitless APIC timer in the beginning. Can you? Yes.
This one?
Yes. Do we have any plans to omit or avoid the exits for programming the APIC timer? So not the firing, handling the firing, but the programming?
There are no such solution, but there are several timer pass-through solutions in by different cloud companies, but they have some limit we can't get a generic solution which can be upstream, but we can have a specific solution by internal use.
So for this, there are two possible solutions. One that I strongly discourage, which is to do IDT shadowing and a lot of ugly stuff, such as in the old exitless interrupt paper, to pass the TSC deadline MSR directly to the guest. And this is possible, but not really recommended. And another possibility, I think, was presented 2 years ago by Alibaba, and it involves having a paravirtualized timer and a CPU that polls on the deadline, injecting the interrupt, so an housekeeping CPU that does polling. And this is actually feasible. The Alibaba patches didn't really go anywhere, but if somebody wants to do it, we can discuss it.
So no more questions.
Okay, thank you.
Yeah, thank you.